Hi, I'm Luke Bennetts. I'm an applied mathematician from the University of Adelaide in Australia. I have particular research interests in water waves and applications in Antarctic science.
And I'm Valerie Pinfield. I'm from Loughborough University in the UK, and I work particularly on ultrasonics for material characterization.
I'm Malte from the University of Augsburg in Germany. I'm an applied mathematician working on multiple wave scattering from a mathematical point of view, as well as in a number of different physics and engineering applications.
So the program is on the mathematical theory and applications of multiple wave scattering. So waves are all around us. They carry energy and information. There are acoustic waves, such as pressure waves in the air when I'm speaking. There are vibrational waves, such as earthquakes in the ground below us. There are electromagnetic waves, such as light waves. And there are water waves, such as surface waves on the ocean, which people can surf on, right up to tsunamis. These waves, they will share a common mathematical foundation despite how different they all are. Now, waves are scattered when they meet bodies. That means that a body can redistribute the waves over different directions. So, for example, sound waves can be scattered by a hard body. Then there are what we call penetrable scatterers. That means that the scatterer supports waves itself. So, for example, think about light going from air through glass. Then there are scatterers that absorb some of the waves. So, for example, there are water wave energy devices which are designed to extract water wave energy for human use. If there are multiple scatterers, then we get multiple scattering, where waves bounce back and forth between the bodies. The waves can add up between the bodies, or they can cancel out. That means that multiple wave scattering gives us a way to manipulate and control the way that wave energy is distributed. Often, there are a large number of very small bodies, and the multiple scattering of those bodies collectively creates a new composite medium. The classic example of that is Bragg scattering of X-rays in crystals, where you get very high reflection at certain frequencies. Now, research on multiple wave scattering has really started to be centered around the different application areas, and it's an aim of our program to bring together researchers from the different application areas who have interests in mathematical techniques and methods to share those mathematical techniques and methods, because those that are developed in a particular application area are very likely to have benefits in all of the other application areas.
Well, waves are very exciting per se. Multiple wave scattering has many applications, which has caused the research in the field to be fragmented, despite the known commonalities at a fundamental level. Researchers in, say, medical imaging, electromagnetics, acoustics, quantum electronic structures, atmospheric imaging, wave structure interactions of different sorts, they often adopt or develop related techniques. But communication between the disciplines has become limited and is often challenging. So there's a strong need to bring together mathematicians, physicists, engineers across diverse disciplines to touch base. We aim to build on shared fundamentals, highlight most pressing research challenges, and exchange state-of-the-art methodologies and approaches. This all-community approach will promote solutions to the current issues facing many practical applications in complex media through the rigorous underpinning of mathematical techniques and the development of efficient computational methods. Well, contemporary mathematical challenges are extensive, ranging from design of metamaterials to numerical difficulties associated with method scattering simulations. The program will be an interdisciplinary joining of forces to elucidate the fundamental mathematical aspects of multiple wave scattering in a variety of contexts, aiming for a deep understanding of the commonalities. Let me give you an example. So, for instance, even in the case of metamaterials, there will always exist some imperfection in the fabricated structures. So metamaterials rely on effects emerging from the structure of the artificial crystals as well as the properties of the scatterers. So geometric mathematical idealizations are not always reproducible in the fabrication process, and flaws exist in real materials, for instance caused by production precision at small scales. So there's an essential pressing question how stable effects are with respect to random perturbations. On the other hand, natural materials are often approximated as having a specific structure, for instance periodic, to make the problems amenable to powerful, analytical or numerical, solution methods, even though they do not genuinely possess the structure. Think of porous media or vast fields of ice flows in the marginal ice zones. So sometimes these approximations lead to very good results, have proven to be very powerful. On the other hand, sometimes they give entirely wrong answers. And therefore, it is indispensable to understand the limits of the theories and of the methods. And so we're very interested in bringing together these communities and to talk about these limitations and to find out when methods work, when they do not work, what the limits are. And so these issues really arise in all application fields as photonics, phononics, acoustics, elastic crystals, water waves, and so on.
So as Malte has explored a little bit already, one of the main aims of the programme is actually to bring people together, to work together and discuss the variety of methods that exist in multiple wave scattering through this variety of applications and disciplines that exist in this community. So the aim is really to bring people together, and through discussion and through collaboration and communication we can learn from each other and really to pick up the commonalities between these methods and identify those key differences. And one of the points of doing that is really to identify the best approach for any one of these particular problems, many of which have been mentioned already, for example, in the metamaterials area. And so it's about identifying what is our best strategy to make the most rapid progress towards solving some of these big problems, which will in themselves result in new technologies that can make a difference in our lives, in our day-to-day lives in the future. So perhaps we ought to mention what some of these methods are. So we're thinking about homogenization techniques, multipole expansions, we've got spectral methods and eigenfunction methods in there too. And of course we're also exploring inverse problems, which are of great importance, for example, in imaging applications. And throughout all of these methods we have of course got numerical methods alongside the analytical techniques, and those numerical methods in themselves are in development all of the time and are very closely linked to the analytical methodologies as well. So let's just mention three specific areas which are challenges in wave scattering. One that Malte has explored a little bit already is the issue of structure. So this is about correlations between scatterer positions, and that affects things like the closure assumptions that we make when applying our mathematical techniques. But also we want to explore issues of disorder, degrees of disorder in our materials. To what extent is a periodic structure important, or a partial disorder or partial non-uniformity? How does that affect our mathematical solution and strategies? The second would be in terms of approximations. We're very familiar with either short wavelength or long wavelength approximations, particularly, for example, in optics where we have Mie theory, and we often talk about Rayleigh scattering in the long wavelength limit. But of course many of the problems that we're interested in fall in that very tricky mid-wavelength region, and that causes us a whole lot of problems. So understanding the limitations of the approximate theories is really important, and developing new strategies for those more difficult problems in the mid-wavelength region is also really important. And my final one to bring in would be the inverse problems as well, which I've already mentioned are really important for material characterization, for imaging, and, for example, for design of metamaterials. We know we can predict how waves propagate through certain materials when we know the material structure, but can we say, in order to achieve a particular wave property, wave propagation property, how do we design the material that will achieve that? So these inverse problems can be very difficult to tackle as well.
During the programme, we are starting with a winter school for early career researchers. We're then running 4 week-long workshops. In between these events, we are also running weekly seminar series as well as informal talks, particularly giving presentations by early career researchers.
So I think one of the most exciting aspects of the programme is the fact that we're bringing together experts in the field who've been working in wave scattering for decades, alongside PhD students who are just starting their research journey, and they can really learn from these more senior researchers and gain the knowledge that they've built up over their working lives in this field. So that's a part of the programme that I personally enjoy and most of all.
Right. And I would also like to mention the industry involvement through the Newton Gateway event that we're planning, so we really look forward to the rest of the programme.